Hi everyone, welcome to the next lesson on motion with variable force. So we saw last time that we could use Newton's second law, the sum of the forces equaled mass by acceleration. And we also saw how we could use acceleration equaled dv dt. Now sometimes we don't get acceleration given as a function of time. So it's handy to have an alternative for this acceleration expression. So imagine please, using the chain rule, that I leave my dt where it is and I just slide the dv sideways. So that's still dv over dt, and I will introduce dx in both of these spaces. dx dt, as you will recall, is velocity. So there's an alternative expression that we can use for acceleration, which is quite handy sometimes. Now, occasionally, we would write this as the derivative with respect to v of 1/2 v squared multiplied by dv dx. And as you can see, there are two dv's, one in the numerator, one in the denominator. So this is an alternative form that we can use for acceleration. Now, do I ever memorize? Well, I don't memorize the last one. I do remember the second one, and of course I remember the original definition of acceleration, and of course I will always remember that the definition of velocity is dx over dt, and that was used in the second step there. So I think you'll find all of those are on your formula sheet. Now let's see if we can do a question involving one of these alternate expressions for acceleration. So here we go. I will read the question. A 2 kilogram mass, m equals 2 kilograms, is moving forward in a straight line. It is acted upon by a force that is F equals the cosine of x, where x is the displacement at a time t and F is in newtons. Part A, find an equation for the acceleration of the mass. Alright, well, Newton's second law then. M times A equals cosine of x. M is 2, so if I divide by 2, that's the same as 1/2 multiplied by the cosine of x. Acceleration equals 1/2 cosine x. I have found an equation for acceleration. Part B, we need to use that to determine the velocity of the particle, and they've told me the initial velocity is 4, so I'll make a note of that. The v0, or v at time 0, was 4. So notice this time we have acceleration as a function of x. I could write dv dt equals 1/2 cosine of x, but then I have a mismatch. I have x as a pronumeral and I have dt as an infinitesimal. They don't match. That wasn't a very good choice. I don't think I want to write dv over dt. Ideally, I would like to have something involving a dx. So let's just go back to where we were. This one involves a dx, so does the one at the bottom, but this one I think is just as good. So I could write v by dv over dx instead of acceleration. How's that? I now have a match. I have the infinitesimal dx and the variable x. I have the infinitesimal dv and the variable v. So this is a nicely formed differential equation. V dv equals 1/2 cosine of x dx. We can integrate both sides of this equation. The integral of v is v squared over 2. Now that's more or less the step that I took to get to this version of the same equation. So you can see why I use the second one, and I just do that integration step as part of my answer. So I have a 1/2 sitting here watching. What is the integral of cosine x? That is sine x plus a constant of integration. I think I should multiply by 2, so I'll have v squared equals 2 times that is just sine x plus just a different constant. 2 times c is, let's just call that c1. And now might be a good time to evaluate. Let's call this equation 1, and we will substitute the initial value we were given was v naught equaled 4. So I'll write that down. So 4 squared would equal the sine of 0 for time. Did they say, what did they say? They said the expression for velocity, the initial velocity is 4. I'm going to assume, okay, they didn't explicitly tell me this, but I am going to assume that the original position equals 0, so that I can put 0 for x rather than 0 for time. Otherwise, it would be a little bit difficult to proceed. So sine of 0 is 0. Therefore, C1, I think, is 16. My answer then, from step 1, I had v squared equals the sine of x, and I'll put 16 instead of the constant. V, therefore, is the square root of sine x plus 16. And that's how we use an alternative expression here, where I've got the green and the yellow highlight, for acceleration. Why did I pick that alternate expression? Because in this step I had acceleration as a function of x instead of a function of time. That's what prompted me to use the alternate version. Thanks for watching.